All right, stats. How are we? I'm making this video on a Wednesday, and I'm gonna make both your Wednesday or Thursday and Friday video now. So this is it. This is my last two videos. This will be 40, actually 41 videos in total over this 11-day absence. 11 school days, that is. All right, so looking forward to seeing you on the 1st, on Monday. I will be there. You might see me on Friday. On Friday, I am going to bring some stuff back. I need to practice getting in and out of the car, and, I need to drop off a lot of stuff at school. So my Monday journey is a little bit easier. All right, folks, so good job watching the notes. Let's keep it up. There's going to be some more Chapter 12 notes, some pretty interesting ones when I get back. I will locate those, and yeah. All right. So remember, this is Thursday's video. So yes, it's being uploaded Wednesday, but your homework was due Wednesday night at midnight. I have received 2 homework sets thus far when I'm making the video at 9:30 a.m. on Wednesday. So hopefully I got 21 of them on time. All right, so go to page 21. It's 1231 there. It's talking about Princeton and Stanford, this individual. His probability of getting to Stanford of 0.4. Princeton 0.4. Probability of getting to Stanford of 0.5. And then probability they get into both, the intersection, is 0.2. Now we're going to talk about the actual independence. Well, I give you independence questions, which could be the hardest ones. We're going to talk about that when I return. I'm going to save the independent notes for when I return. Okay, so let's make a Venn diagram. So the intersection is 0.2, 0.2, the intersection. Probability they get into Princeton only is 0.4 minus 0.2. Probability they get into Stanford only is 0.5 minus 0.2. Probability they get into none of the schools. Add them up, subtract from 1. Yes, I do need to see this rectangle, okay? Just like I give it right here. So 0.3 is probability they get into 0 schools. So probability of no admittance is 0.3. Probability of Stanford only is 0.2. Probability of Princeton only is 0.3. Probability they get into at least 1 school is 1 minus probability they don't get into any school, 0.7. So I want to know, are they independent events? Well, as you guys wrote down, this is, if 2 events are independent, then this is true. The probability of their intersection is equal to the probability of A times probability of B. All right, well, I know what the probability of intersection is 0.2. What's the probability of A? 0.4. What's the probability of B? 0.5. And I put a question mark. I want to know, are they equal? And come on, paper. Yes, they are equal. So yes, they are independent events. The getting to Princeton and Stanford, they are independent events here. All right, so we're gonna go to 1232, folks, which is very timely for me. But we got some sponsors on this last day of videos. Cliff Bar, cool mint chocolate with energy. Speaking of energy, Noon Hydration tablets. And everyone's favorite, Live G Free. Gluten-free chocolate chip soft base baked cookies. Yummy they are. All right. 1232. This was talking about surgery. Tendon surgery. I've learned about tendon surgery. That is a big deal. Like, that is a long recovery. That is tough. So some things we want to avoid. 1232 says exactly this. So all right. Tendon surgery. You have torn a tendon and are facing surgery to repair it. The surgeon explains the risks to you. Infection occurs in 3% of the operations. We don't want that. The surgery just fails, like it doesn't work in 14%. That would be bad. And both infection and failure occur in 1%. That's ultimate bummer. What percent of these operations succeed and are free from infection? we would call that total success. What's the probability of total success? It's 1 minus the probability of anything bad happening. And I'm going to say that something that bad happens would be an infection or it fails. So the probability of bad is infection plus it fails minus the intersection. So the probability of bad is 0.16. So the probability of total success is 1 minus 0.16, 0.84, 0.84. All right, 0.84. There we go. Very interesting question there. All right, and they do know they have enough. Get some emails here. They do know the chance of recurrence for certain things. I've become very familiar with that, with different bone cysts and potential of what that could have been in my foot. So yeah, you can look that stuff up. All right, that's a nice thing. Like Google, wow, just an unbelievable time to find out stuff. All right, find stuff out on the interwebs. All right, so here's what we got on 1234. Choose a student in grades 9 through 12 at random and ask if he or she is studying a language other than English. Here's the distribution of results. Okay, so none means they're not taking a foreign language. All right, Spanish, that's the most popular one. Most schools have Spanish. Some schools have French. Some have German. Some have all three. We had many Spanish teachers when I was in high school, and I think we had one French teacher and we had one German teacher. I think actually the French teacher might have taught Spanish as well. So those are to a lesser extent. But German would probably be the next. I'm surprised. I think German would be the next popular one. Anyway, so what's the probability that they are studying Spanish given that they are taking a foreign language or studying something other than English? So given that they are studying something other than English is 1 minus this. That's why the denominator is 0.41 and they're studying Spanish. So 0.26 out of 0.41 is that. You need to write a probability statement. Probability of Spanish given language other than English. All right? Doesn't have to be an essay. Just tell me what we're looking at. Again, the given always goes second after that vertical line. Now we talk about income tax returns. So here's the distribution of adjusted gross income, all right? Because you, on your income taxes, you want to look like you make less, okay? So, you know, on my salary, they take 9% out right away for retirement, TRS, for like that pension program. So, you know, that my adjusted income looks 9% less than what it is. Then you can also, like if I'm filing with my wife, which we do joint, so we wouldn't be in the individual. I think this is talking solely on individual federal income tax returns, though they might be looking at single, I don't know. I would assume individual means you're filing individually, all right? Joint, you're filing, you know, as a couple. So then you can get deductions. I mean, if you pay for daycare, if you do just certain things, you can deduct. You want on your tax returns to go into drop a tax bracket. Okay, you want to have as many deductions as possible. All right, so let's assume though, I don't know. We're looking though. I guess I could tax return in 2015. That's 16 years. The median family income now is $63,000, but that's a family. This is only 31%. So I could see how this could be maybe an individual. All right. So what's the probability that a randomly chosen return shows an adjusted gross income of $50,000 or more? So I said that X was the income. What's the probability that X is greater than or equal to 50? You do this plus this plus this. Boom. Then the next one says, given that a return shows an income of at least $50,000, that's the denominator. What's the probability that they make at least $100,000? So it would be this plus this over this. All right, what's the probability that X is greater than or equal to 100, given that it's greater than or equal to 50? B, you got to write those probability statements. Okay, you got to write probability statements. Especially on your homework, got to write probability statements. All right, going to need those. You can be marked off like if you don't write a probability statement. That can happen. Okay, we got an interesting case of conditional probability. Probability teaser. Suppose, as is roughly correct, that each child born is equally likely to be a boy or girl, and the sexes of successive children are independent. Though there's plenty of families that have, nothing but boys or nothing but girls. Anyway, if we let BG mean that the older child is a boy and the younger child is a girl, so in order of that's the order of the kids that they had, then each of the combination is a BB, BG, GB, GG has a probability of 0.25. Ashley and Brianna each have 2 children. Ashley has 2 kids. Brianna has 2 kids. You know that at least one of Ashley's children is a boy. What's the conditional probability that she has 2 boys? So what's the probability that Ashley has 2 boys given at least one is a boy? Well, this can't happen then for her. She can't have 2 girls. So there's 3 total possibilities. And one of them has 2 boys. 0.3 repeated. What else? You know that Brianna's older child is a boy. What's the probability that she has 2 boys? So you know that this is the case. The older child is a boy. So there's 2 possibilities. And one of the possibilities would have 2 boys. So 0.5. All right, let's talk about college degrees. We've examined this before. This has kind of been a thing going on right now. A striking trend in higher education is more women than men reach each level of attainment. How are the counts in thousands of earned degrees? Oh, here are the counts of thousands of earned degrees in the academic year that I graduated college. Interesting. 2010 to 2011. So I wrote that out again for us. Zoom out. So female, male, bachelor's, BA, BS. It's either arts or science. MA, MS, arts or science. Professional degree, which I'm interested in what that is. Doctorate. Now, so doctorate in this, I don't think they're talking about MD. I think they're talking about pure PhD in anything. So maybe professional degree would be like a law degree, Juris Doctorate. Though Juris Doctorate, that's a JD. The past pharmacy degree before they now get, I think, PhDs as well. And that, I said law school, medical school. I'm thinking something like that. Those are professional degrees. I'm thinking. I don't know. Again, this is in the thousands. So this is in that year, 2.5 million people were awarded some sort of degree. So A says if you choose a degree recipient at random, what's the probability that they are a woman? So it's just the probability of a woman getting a degree. You use that as the denominator and how many women there are. All right, so almost 60%. I think it's been close to 60% for a while. All right, and then it says, what is the conditional probability you choose a woman given that they received a doctorate? So probability of woman given it's a doctorate. So doctorate, 59 needs to be the denominator, and 32 is the numerator. Okay. Getting just a bunch of emails here at once. No biggie. So, 1240. College degrees again. So we're just going to keep answering some questions. The first one was like, what's the probability of choosing a male that got a degree? So how many men? You're going to do that over that. And given that it's a male that earned a degree, what's the probability that they earned a bachelor's? Okay, so again, males would be at the bottom. And how many men earned a bachelor's? There you go. You can see that, bachelor's degrees, what is that? Are they over 2/3? 2/3 of degrees? That kind of makes sense. All right. Let's go. That was 1240. So we now are going to go to the bottom of page 23. And this individual was applying to jobs. All right. Criminal background jobs. So there is no chance of all 3 offering a job. And then I just put this in there. So you're given that, again, Probability of A and C, A and B and C. Probability of A alone is 0.6 minus the other, these three. Probability of B alone is 0.4 minus this, and this. Probability of C alone is 0.2 minus this, and this. So probability of no jobs is 0. He's going to get a job. Probability of no offers is 0, but probability of all 3 offers is 0. All right, so what's the probability of at least 1 offer? I'm sorry, of only 1 offer. Like, she's getting an offer. Probability of at least 1 offer is 1. Probability that she of just only 1 offer would be that, and that. Probability that only one of these offers her job is 0.80. Probability of at least 2 offers is this, and this. Added up. Probability of no offers is 0. Just wanted to write that out. All right, there we go. And I'm going to finish it up here. We're just continuing. Go to 1247. 1247. Geometric distribution. So you're going to toss a pair of balanced dice in a board game. Tosses are independent. You land in the danger zone that requires you to roll doubles. You have to roll doubles before you're allowed to play again. Uh-oh. All right, so doubles. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. 6 of the 36 sums. All right, what's the probability that, so that's probability of getting double. What's the probability that you don't roll doubles on the first one, but you roll it on the second one? So what's the probability of no doubles? Doubles. 5, 6 times 1, 6. And then it wants to know what's the probability that the first 2 are not doubles, but then the third one is. So probability of no doubles, doubles, or failure, success. Okay, so you kind of see, you can get the pattern here. What's the probability that your first success, your first doubles is on the 4th trial? That means you fail 3 straight times, followed by success. So when we actually talk about the geometric distribution in chapter 13, it'll be what's the probability that your first success is on the 4th one or the 5th one? You fail 3 straight times and then you succeed, and it's whatever that is, 125 over 2196. Is that what 36 to the 4th is? Or 36 squared. Yeah, I'm sorry, 1296. Goodness. 125 over 1296. We'll talk more about the geometric distribution later. Okay, we're going to end on this tree diagram. So sometimes you'll make tree diagrams. I tutored plenty of students in stats. As I told you in college, tree diagrams were a thing. This is an odd tree. Okay, so we're a player serving in tennis has 2 chances to get a serve into play. If the first serve is out, the player serves again. If the second serve is also out, the player loses the point. Here are the probabilities based on 4 years of the Wimbledon Championship. All right. So here's what a tree diagram does. So obviously you got a tree. Branches are going to be different because if you get the first serve based upon whether the first serve is in or out. So you start with what's happening with the first serve. The first serve is in versus the first serve is out. So the first serve is in with probability of 0.59. The serve is either in or out. So you can confidently say that the first serve is out, probability 0.41. You're going to multiply these little limbs here, okay? What do they call them? The branches. Okay, so then it says the probability that you win the point, given that the first serve is in, is 0.73. So how did I get this number? And you win the point. We want to know what's the probability of winning the point. So what you do is you multiply 0.59 times 0.73. So there's a 0.431 probability that you win the first point, that the first serve goes in and you win the point. That happens in 0.431 with 0.431 probability. All right. So then what happens? Well, you get the first serve in, you win the point, but you can also lose the point. So given that the first serve, the probability that you lose a point given that the first serve is in, what you're going to do is you're going to multiply these two together, 0.59 times 0.27, and you can just do this with general multiplication off to the side. You don't really need a tree diagram. Made very few of them, and you won't need one in my class, but this is what's going to happen. So you lose the point, they lose this point, and given that the first serve is in, you lose the point with a probability of 0.59. So either first serve's in, you win the point, or you lose the point. Okay, so then what's going to happen? First serve is out. First serve is out with probability of 0.41. So the second serve is in, given that the first serve is out. 0.41 times 0.86. So the probability that you win the first serve, given that the first serve is out and the second serve is in, is 0.59. So first serve is out, second one is in, but you win that one. What are you going to do? Multiply this by this by this. So the probability that you win the point, given that the first serve is out but the second serve is in, is 0.208. All right, so let's go here. First serve is in, second serve is in, but you lose the point. Well, if you win the point with probability of 0.59, you lose the point with probability of 0.41. So 0.41 times 0.86 times 0.41, the probability that you that's the first serve is out, second serve is in, but you lose the point, is 0.145. So all these give like exact situations. First serve is in and you win the point. First serve is in and you lose the point. All right. And then lastly, the ultimate bummer, the first serve is out and the second serve is out. Well, that's, what is that, double fault? You lose a point. 0.41 times 0.14. It's probability that two serves are out, 0.057. That is all the scenarios that can happen. So the probability that this person wins the point would be this plus this, 0.639. I believe we're right. If you add up all the probabilities, you get 1. And someone's got to have it with probability of 1. You win the point or lose the point with probability of 1. There's no tied points. Okay, that was a fun one. Anyway, we're gonna start Friday's notes with the birthday question. That's a good one. All right, folks, this is your second to last notes video, and this is Yak Math Videos signing out.